Okay, so once again, thanks, Dr. Indulal and his colleagues for giving me this opportunity. So, so let me begin my presentation. So, as all of you know, a large part of mathematics has its roots in physics. So, let me begin with a couple of motivating problems in physics before going to our conventional introduction to function analysis stuff. Okay, so these are some couple of familiar problems to all of you. So usually in an undergraduate course, we come across such problems. The first one is the vibrating string problem, and the second one is the heat conduction problem. So let me explain it in very brief. So okay, so let us consider the vibrating string problem first. So suppose an elastic string is tied, keep both ends fixed, and you just pluck it or struck it, so then it starts vibrating. Okay, so so we need to understand this vibration. So suppose the function y xt represents this the position of this string at the point x and at time t. I mean, let us assume that the string is at the one end point of the string is at the origin 0 and the other end point is at 1. It's a one-dimensional string. So neglect the thickness of the string. And it starts vibrating. So as time progresses, it will depend on the time also, the position. So y will be a function of x and t. And suppose we know the initial position of the string. So that means we know that y equal f of x at time t equal to 0. And you assume that you also know the initial velocity. That means at time t equals 0, the velocity is yt. I mean, the first partial derivative with respect to t. So yt is given by gx. So suppose we know these two things, then by some physics laws, for example, the Newton's second law of motion. So Newton's second law of motion tells you this very simple thing. I mean, it gives you an equation for force and work done, force and equal to some mass into acceleration kind. So using these physical laws, you can derive the system of equations. So what we obtain is this. So this derivation is again something common to the undergrad course in mathematics. So you will obtain this equation, ytt equal to a square into yxx. Whereas the left hand side represents the second partial derivative with respect to t, I mean time, and the right hand side represents the partial derivative with respect to the position x. So this is a well-known wave equation. Okay, and we assume that y0t equal to y1t equal to 0. That means the boundary condition. So once you fix the endpoints, I mean 0 and 1 is fixed. So there is no motion at all. So therefore, that y at 0t and y at 1t will be 0. So we can also consider other cases where only one endpoint is fixed and other allowed to vibrate and so on. So in this case, if you keep both ends fixed, then you will have y0t and y1t equal to 0. And the initial conditions, as I mentioned here, so the initial position is supposed to be known to us, is given by f of x, and the initial velocity is assumed to be g of x. So this is our problem. So by a vibrating string problem, if we want to understand the vibration of this string, we need to solve these problems. I mean, we need to solve this equation, wave equation, with the boundary conditions and initial conditions given by this. Okay. Now let us look at the solutions. So it's a simple computation, and you will see that these two functions, I mean yxt given by sine k pi x into sine ak pi t, and yxt given by sine k pi x into cos ak pi t will satisfy the equations and boundary conditions. That is very easy to check. But the initial conditions need not be satisfied for all choice of f and g. So there will be some restriction on the initial conditions. That means you cannot have a solution with an arbitrary f and arbitrary g. So the initial velocity and initial position is determined by this. Okay. Now these are solutions, and by kind of linearity of this problem, you can easily see that any finite linear combination of these two solutions, I mean this one and this one, you take any finite linear combination of them, that will also satisfy this equation. So that is very easy because our problem is linear in some sense. So it will also satisfy the boundary conditions, but of course you know that there will be restriction for the initial conditions. Now the natural question is, what happens if we consider an infinite linear combinations? I put in the inverted comma because for the time being we don't know what is meant by an infinite linear combination. So we can add these functions, that's all. So you don't know what a convergence notion and all these things for the time being. Okay. So this is the question arises quite naturally from this problem. Okay. So now I think you understand that the problem is to consider the infinite series of this form. Okay. Now let me consider another problem related to the same thing, something called as heat conduction problem. So here what happens, you imagine a thin plate of some material and you apply heat from the boundary, and the natural Newton's law of cooling will tell you that heat flows from a point high, at the higher temperature to a point at lower temperature. That is quite natural. So that is Newton's law of cooling. And you assume that, so you are having a thin plate, a two-dimensional object. You assume that the temperature at the point xy is denoted by u of xy. So it's a function of position. It will also depend on time. But let us assume that it is a kind of steady state. So we need to understand the temperature at an arbitrary point, xy. That means you need to understand the function u xy. So that's the thing. Okay. Yeah. Now, with some physical experiments, I mean experimental facts, and using this Newton's law of cooling, we obtain the heat conduction at steady state. Steady state is important. That means I just neglect the independence of time. I assume that it is independent of time. So then we will see that it is governed by the following equations. So you'll obtain that it satisfies, this u satisfies this partial differential equation, dou square u by dou x square plus dou square u by dou y square equals 0. This is the Laplace equation, well-known Laplace equation. And if you write it in the polar form, so we are in the two-dimensional plane. So this is the equation in Cartesian coordinates. So if you replace by the polar form, you will obtain this. That means dou square u by dou r square plus 1 by r and dou u by dou r plus 1 by r square into dou square u by dou theta square equal to 0. Now, now suppose we consider a special situation where your plate is a circular disk. Okay. Maybe you can consider unit disk. So it is modeled by a unit disk. Okay. So what happens? Suppose the heat flow at the boundary is given. So that is typically that is the situation. We know the heat conduction at the boundary. So we are applying heat at the boundary. We need to know the heat at a certain point. Okay. So that means at the boundary means u1 theta. I mean the boundary of the circular disk is when r equal to 1. So that is given to us. So u1 theta is f theta. This is the boundary condition. And this is the natural condition satisfied by u because r theta plus 2 pi and r theta represent the same point. So u r theta plus 2 pi should be u r theta. That means periodicity comes quite naturally. So we need to solve the equation with satisfying these two boundary conditions. These two conditions. One of them are boundary conditions. Now, again, there's a typical method called variable separation method, where you assume that u is of the form f of r into, say, g of theta, and this is due to Hilbert. So after doing all those computations in partial differential equations, you'll obtain that u n r theta given by a r raised to n into capital A e power I n theta plus capital B e power minus I n theta, where n varying in the set of natural numbers, and these A, B are constants. These are solutions. This will solve the Laplace equation. Okay, so that is very easy to obtain. I mean, let me not do the computations here. Now, once these are solutions, and again by the linearity of the problem, you will see that any finite linear combinations of this form. So here you can see that n varies from minus n to positive n, minus capital N to positive n. These are constants, capital N's are constants, and r power mod n e raised to in theta. This will also satisfy the equation. Okay. Now here, if you apply the boundary condition, so this is a solution, say u r theta. So at boundary, it is u1 theta, and the boundary condition is given to be u1 theta to be f theta. Remember that boundary condition is u1 theta is given to be f theta. So if you apply the boundary condition, it should be f theta should give u1 theta, and if you apply it here, you will obtain that this is this finite linear combination of exponentials, the trigonometric functions. So f of theta should be minus n to n a n e raised to in theta. So now again we ask the same question. Okay. So now this tells you something more. Actually, this tells you that the boundary values f theta need not be arbitrary because it is constrained by this condition. And the right hand side, you know that you have a periodicity here. So f has to satisfy something like that. Okay, it cannot be arbitrary. Now again, the natural question: what happens if we consider infinite linear combinations? That means f theta of this form. So we may require something like this, but there is no meaning of convergence here for the time being. We don't know. In fact, these couple of problems are the origin of Fourier series. So the last one is known as Fourier series. And at some point of time, people believed that this series is a solution for every choice of ANs and all. And every boundary condition, given boundary condition, you will have solution like this. And what I want to convey is that this comes from a purely physical problem, but those times people were not bothered about the convergence issues and all. Okay? So later, when the mathematics, the calculus was made rigorous by doing some analysis, modern analysis, then these kind of issues, convergence issues of Fourier series and all other things came into picture. Okay, and one thing is that the mere convergence issue of Fourier series contributed a lot to the development of classical analysis, which we learn now. Now let me again mention some other areas where the function analysis tools are being applied to a large extent. So let me not pretend to know all these areas, but let me just list down them. Again, this list is not complete. Signal processing is another area. That is something quite popular to all of you. You use Fourier transformation and Fourier series to reconstruct a signal which is sent from some place to another place. And data compression issue, of course, it is there. Now, the tomographic reconstruction means it's a kind of inverse partial differential equation problem. Just like if you look at some mining problem and all, you know the information of the boundary and you want to know something in the interior. So that comes quite naturally here. Principal component analysis is much popular now using linear algebraic tools. Machine learning, then probability theory, of course. Now let me come to the geometry business. So this is something quite familiar to all of you again. Our basic high school geometry, the Pythagorean theorem tells you that for a right angle triangle, this is a right angle triangle, you have this, s square equal to b square plus h square. And a parallelogram law, which tells you that if you consider a parallelogram with sides L1 and L2, then the diagonals D1 and D2, so then it satisfies this law, D1 square plus D2 square equal to 2 into L1 square plus L2 square. So now, what I want to convey is that, see, these are two algebraic identities, either the Pythagorean theorem or the parallelogram law. So they are output of some geometrical considerations. So one is the reason for the first identity is the angle between these two sides are theta, I mean pi by 2. And here it is due to the parallelogram thing, which means these two sides are parallel to each other. Okay. So we observe that both these algebraic identities are the consequence of certain geometric properties. Okay. So the angle between two vectors is core notion behind these ideas. So now let us look at the relation between angle and dot product. So consider the dot product between two vectors A and B. So dot product is defined by A dot B equal to the magnitude of A into magnitude of B into cos theta, where theta is the angle between A and B. Okay. Now with this identity, look at this identity. You can retrieve theta back. If A and B are non-zero, theta is cosine inverse of this. Okay. That means you can obtain theta provided you know dot product. So this is the connection between dot product and angle. So angle between two vectors, two non-zero vectors can be obtained provided you know the dot product between those vectors. So that is one important observation. The second thing, you have an algebraic identity satisfied by dot product. So A dot B is obtained by A1 B1 plus A2 B2, where A is given by this vector, this coordinates, and B is given by this. So what is important is that the left-hand side A dot B is, we have seen that comes from the geometry using the angle between these two vectors. But the right-hand side is only an algebraic thing. I mean, it makes use of only the algebraic operations. Okay, and therefore the right-hand side you can generalize it into higher dimensions. Wherever this algebraic operation makes sense, you can generalize this notion. So via this identity, we can generalize the dot product to higher dimensions. So that is our idea. And again, from the previous slide, we have seen that if you are able to generalize the dot product, from this identity, you can also generalize the angle between two vectors. So naturally, we are generalizing we are carrying over this geometry to higher dimensions using this dot product. That's our idea. So our idea is to use the dot product in higher dimension and carry over this idea of angle to the higher dimension. Now, there's one thing you have to keep in your mind in case of complex case. Suppose these vectors considering A1, A2 and B1, B2 can be complex numbers. Then what happens? You consider a very important property of dot product. That means A dot A is given by mod A square. Okay, so this is a connection between dot product and the magnitude of a vector. Okay, so once we consider with complex entries, if you need this property to be satisfied, then you need to take the conjugate here. So that's why when you are having complex vectors here, then A dot B should be defined as A1 bar B1 plus A2 bar B2, where this bar denotes the complex conjugate. Otherwise, you will not get this identity. So that is something you can easily verify using some simple vectors like 1i or something. Okay. Now another thing, it's an alert. Most of the mathematics textbooks introduce conjugation at the second variable. I mean, typically conjugation is given at the B1 part and B2 part in the typical mathematics book. But notation from mathematical physicists are as given here. Okay, so now I am following a mathematical physics textbook. That's why I gave this definition. But in fact, it will not make any difference, except that if you are starting with this definition, your linearity will be in the second variable, and if you are doing the other definition, linearity will be in the first variable. So that's the only difference. But essentially, all the results will be the same. Okay. Now, before going to the formal definition, let me discuss some examples. Okay. Our first example is H is equal to Cn. So Cn means you collect all n tuples of complex numbers Z1 up to Zn, with Zi belongs to Z. And you know that it is a vector space with the typical usual addition, vector addition. I mean, component-wise addition and scalar multiplication. I mean, you can add two vectors component-wise, and you can multiply by a complex number again component-wise. Okay, that will satisfy all the axioms of a vector space. So this is a complex vector space. So Cn is a complex vector space with the usual the component-wise addition and scalar multiplication. Now on Cn, let me define a product. I mean an inner product. I mean something like a dot product. That means for Zw belongs to H, we define this notation is used for dot product or inner product in general. This inner product Zw is defined to be summation j equal to 1 to n Zj bar Wj. This is exactly the generalization of what I given for dot product. Look at the 2. So this is n equal to 2 case. So you have a1 bar a1 b1 plus a2 bar b2. If n is greater than 2, you will have a sum up to n. That's the thing. So that's why set W is defined by this. Now we shall verify these three properties. That is very easy. The first one is its linearity in the second variable. So if you take inner product Z with alpha 1 W1 plus alpha 2 W2, then you can take this sum outside. That means alpha 1 will come out and you'll have set W1, alpha 2 will come and you have set W2. So that means here if you have a finite sum, finite linear sum, that summation you can take outside and you will have set WJ. That's the meaning of that, the first expression. Second thing is, so this is very easy because you just go to the definition. So this will be affected here and you can take alpha 1 and alpha 2 outside and so on. It's a simple exercise. Now another thing is that set W, if you replace by WZ, if you change the order, then you can immediately see that the conjugation will change. So there will be a conjugation here. So set W equal to WZ bar. This is not a conjugacy. So now with the second property and the first property, if you club them together, you will see that you have kind of linearity in the second variable also. If you put this in the second variable, in the first variable, if you put it in the first variable, you will have the same thing, but the only thing is that because of this conjugation, instead of alpha 1 bar will come outside. Instead of alpha 2 bar will come outside. So that's the only difference if you try for linearity in the first variable. So that is known as conjugate linearity or anti-linearity. So this is linear in the second variable and anti-linear in the first variable. Now the third property, that is again immediate. If you take inner product Z with Z, then what happens here? It will be Zj bar with Zj. That means absolute value of Zj bar, Zj square. So sum of non-negative terms, it is always non-negative. So Z will be always non-negative. Now suppose it is 0. It is 0 means sum of non-negative terms are 0 means each term should be 0. Therefore, each Zj should be 0. That means Z equals 0. So what you have is that inner product set Z equals 0 only when Z equals 0. Now there's a small catch. This 0 is the number 0. And this 0 is the 0 in the vector space Zn. That means it is a vector with each entry 0, 0, 0, 0. So that's the difference here. So these three properties are satisfied by this function inner product Z W. Okay. Now let us look at the second example. Now so far we have been dealing with finite n tuples. Now we deal with infinite n tuples. So you take infinite sequences of complex numbers, but we demand that there are only finitely many non-zero things in each vector. So that is C00. That means it's an infinite, all infinite sequences such that Zi equals 0 except for finitely many I. So except for finitely many i's, there will be 0. So there will be only finitely many non-zero terms in this sequence. Now again here also we just imitate what we did here. You define inner product ZW here by imitating the definition in the finite case. Now you have an infinite sum because there are infinitely many terms. But here you don't have to worry about the convergence because even though it is an infinite sum, there will be only finitely many non-zero terms because Z and W are coming from C00. So only finitely many Zj's are non-zero and only finitely many Wj's are non-zero. So only finitely many terms in this series will be non-zero. Therefore, it reduces to a finite sum always. So you don't have to worry about the convergence issues. So this is well defined. Now, once the convergence is not a botheration, proving this properties 1 to 3 is easy because you can just imitate what you did in the finite case. Okay, because it's a finite sum only. So 1 to 3 is easily verified. Now let us go to the next example. Here we consider again infinite case, infinite sequences. But if you consider all the infinite sequences and define the inner product in the similar way, suppose we define it like this, then there is a convergence issue because we have infinite sequence here. So this series will be infinite and there will be non-zero terms, infinitely many non-zero terms. So we need convergence of this series to make sense of this inner product ZW. Therefore, we give a restriction here. we don't consider all infinite sequences. Instead, we demand that all infinite sequences with this square summability. We demand that summation j equal to 1 to infinity mod z j square is finite. This is important, and as a consequence of this condition, you will obtain that this series is convergent. Okay, so once such a convergence is established, then again it's an easy thing to verify the property 1 to 3. That means these three properties you can verify easily. The only thing is that instead of a finite sum, you will have an infinite sum here, but convergences are already taken care, then it is easy. So this is a very important Hilbert, later we will prove that it's a Hilbert, later we see that it's known as Hilbert space. This is a very important space, L to N. Okay. Now let me continue the example. So now, so far we have been considering with the sequence spaces. Now this is a function space. So you consider x equal to C01. So what is C01? You collect all functions from closed interval 01 such that they are continuous. So we take only continuous functions defined on 01, the closed interval 01. And we define, f and g, so you take f and g from C01. F and g are continuous. So therefore this quantity is also continuous. F bar g is also continuous. So you have a continuous function on closed interval 01. Therefore you have the typical Riemann integration now. So you can consider the Riemann integration of that. So you don't have to worry about the extents because every continuous function on a closed and bounded interval is Riemann integral. So you consider the Riemann integral of f bar g. So this is how do we define inner product f g here. This is again quite natural. You can see the earlier definition was summation. For finite n-tuples you have finite sum. For infinite n-tuples you have infinite sum. So now you are dealing with functions means this is a special case of that, right? So sequence is a special kind of functions. So functions means we are dealing with uncountable things. So it will be an uncountable sum. That is what we call an integral. So this is how it comes quite naturally. You have an integral here. So you know that Riemann integration is linear. So, and also it is positive. Positive in the sense if f greater than or equal to 0, then integral f greater than or equal to 0. So these two properties will give you the property 1 to 3, but you have to do some work on this property. This property. This will be non-negative always, but if you want to obtain f of equal to 0 only when z equal f equal to 0, you have to do a little bit work. What do you have to do? So suppose f of equal to 0. F of means integral 0 to 1 f bar f. That means integral 0 to 1 mod f square. So the question is whether integral f equal to 0 implies f equal to 0. The answer is no. You have examples where integral is 0 even though function is not 0. What happens if you have continuity? Then also you have answer is no. You can consider, for example, sin x and all interval. Its integral vanishes because you have oscillation. So if you don't have oscillation and continuity, that means function is non-negative and integral vanishes, then you have function is 0. Because if function is non-zero, then there is and it is positive, non-negative. So there is at least one point where it is strictly positive, and by continuity you can find a neighborhood where it is positive, and in that neighborhood you can consider the integral will be positive. So the whole integral will be positive. So integral is 0 means function is 0 provided function is continuous and positive. So that can be used to obtain the third property. So this will be satisfying 1 to 3. Now let us go to the most important example. But let me caution you, if you are not familiar with measure theory, you shall just neglect what I am talking about measure and all. But I will not discuss about the measure in detail. But just keep in your mind that on the real line, there is a measure called a Lebesgue measure, which is translation invariant and which has several properties. Okay, and using that measure, you can generalize the notion of Riemann integration to something called Lebesgue integration. Okay, so here I am considering the Lebesgue integral. Okay, so I am considering all functions which are square integrable. Okay, here I am considering the Lebesgue integration with respect to the Lebesgue measure. So square integral means integral mod ft square is finite. But there's a small catch here. in fact, strictly speaking, the elements of L201 are not functions, but equivalence class of functions. Okay, so what do you mean by this equivalence class? So I'm taking the equivalence class F means F and G are the same equivalence class means F equal to G almost everywhere. That means the set where F not equal to G has Lebesgue measure 0. So again, if you are not familiar with Lebesgue measure and all, just skip this example. But this example is important. We'll come back to this again. So just neglect the measure. But that is very important. If you want to learn function analysis, you should know a little bit measure theory. Not little bit, in fact, a lot of measure theory. So L201 is the equivalence class of all functions which are square integrable with respect to the Lebesgue measure. And here again, the definition of inner product is the same. Inner product Fg is F bar G bar. Again, the existence of this integral is a consequence of this condition. So let me not do the technical part, but that is easy. So again, you have all the properties of Riemann integration like linearity, positivity, everything, but up to a set of measure 0. So that is not the problem because the vector 0 here is the set of all functions which vanishes almost everywhere. It is not the 0 function. Here the 0, in this vector space, the 0 is the function which vanishes everywhere. That means f of t equals 0 for all t. But here it is not like that. Here the 0 means it is a 0 class. That means all functions which vanishes almost everywhere. That means in a set of measure 0, it can have non-zero values, no problem. So again, you defined it like this, and it is easy to verify the properties 1 to 3 using all these properties and some properties of Lebesgue measure and Lebesgue integral, which I do not mention here. Okay, now the final example is the familiar one for all of you, the set of all n by n complex matrices. So this is a familiar set, and you know how the linear structure, you can add two matrices and you can multiply by a scalar, everything. Now for A and B in two matrices, you define the inner product to be trace of B A star. Trace means the sum of diagonal entries. You define inner product AB to be trace B A star, and you just verify the property 1 to 3. It is easy now. And in fact, it's a slight cheating. In fact, this example, you can actually identify the example I gave initially. I mean, the first example that you will see maybe later. Okay, with these examples, let me go to the definition. So what do you mean by an inner product space? You consider a complex vector space with an inner product. So what is an inner product? Inner product is a function from this vector space to R, satisfying property 1 to 3. What are the properties? Let me just rewrite again. Linearity in the second variable, that's what I wrote here. You have a linear sum here, you can take that linear sum outside. So linearity in the second variable. And this is anti-linearity, or what you call conjugacy. Fg is equal to gf bar. And this is positivity. That means ff will be always non-negative. And ff equal to 0 only when f equals 0. Again, this 0 is the 0 complex number, the 0 number 0, and this 0 is the 0 in the vector space X. So this is what you call an inner product space. So you have a complex vector space with an inner product, okay, satisfying these three properties. Now, one remark about the first property is that this you can, by mathematical induction, you can do for any finite linear sum. Suppose you replace this by a finite linear sum, summation I equal to 1 to n ai gi, then that summation you can take out. That's the meaning of this. Summation I equal to 1 to n ai into inner product f gi. That's what you can do. You can do it in the first variable also, but when you take out the scalar, we'll have a conjugation because of this. That's the difference. Now, there's a small alert. There is a literature on real inner product space also. So we consider only the spaces of our complex fields due to various reasons. So in general, the definition will be need not be a complex vector space, but a vector space over C or R. But we consider only the complex vector space because of some reasons. Now, let me use a notation here. You know that this inner product FF is always non-negative. So it's a non-negative number, it has a positive square root. So let me call this positive square root, denote this positive square root by this. This is something called norm. But for the time being, it's only a notation. We will not prove anything about this for the time being. I just use this notation norm f for this ff power 1 by 2. That means norm f square is inner product ff. Okay. So now you recall our basic geometry. The dot product a dot a gives you mod a square. That means a dot a power 1 by 2 gives you the magnitude of a. So a vector is something with both magnitude and direction. So the magnitude is obtained by this, right? A dot a power 1 by 2. So in that sense, this should give you the magnitude of f or size of f in the abstract setting. So that is something we will see later. Okay. Now let us prove the classical parallelogram identity. We have observed this for the Euclidean geometry at the beginning. Now you look at here. You start from an inner product space and so look at so one second. Yeah. So you look at the inner product space at X and f and g in X. Then norm f plus g square plus norm f minus g square equal to 2 into norm f square plus norm g square. So this is the parallelogram identity. Why do we call it a parallelogram identity? Because suppose you consider a parallelogram with side f and g, one side f and one side g. So then what happens? It's one diagonal will be f plus g and the other diagonal will be f minus g. That is from the usual law of vector addition. So you put f to the f as one side and g as one side, then the then the diagonal of the parallelogram with sides f and g will be f plus g and f minus g. So therefore, if norm represents the size of the vector, then this represents the square of the length of the first diagonal, and this represents the square of the length of the second diagonal, and this represents the square of the lengths of the sides. So this gives you exactly the Euclidean parallelogram law. Parallelogram law in the Euclidean geometry. Now the proof is very simple. Just use the definition. What is norm f plus g square? By definition, it is f plus g into f plus g. Now you use the linearity in the second variable. So it is f plus g into f plus g into g. Now you use linearity in the first variable. In the first variable, you don't have linearity, you have anti-linearity, but you are not using any scalar here, so you have the same thing. So it will be ff plus gf plus fg plus g. So ff by definition it is norm f square, and gg by definition it is norm g square. Now fg and gf are conjugate to each other, so it is just like z plus z bar. So that is 2 into real part of this. So combining this, you obtain norm f plus g square is equal to this. Norm f square plus norm g square plus 2 into real part of fg. And similar computation will give you norm f minus g all square equal to norm f square plus norm g square minus 2 into real part of fg. Now you just add these two things, you will obtain parallelogram identity. The proof is quite easily done. Now, the notion called orthogonality. So in the classical geometry, Euclidean geometry, we know that two vectors are perpendicular to each other if their dot product is 0. So similarly, you define f and g are orthogonal if f inner product fg is 0. And a collection of vectors f alpha with alpha belongs to identity I in X is said to be orthonormal if their inner product is given by the derived delta function delta alpha beta. What do you mean by this? F alpha with f alpha will be 1 and f alpha with alpha beta will be 0 if alpha not equal to beta. That is a definition. Okay, that means they are orthogonal to each other and their norm will be 1. F alpha will be 1. So that is the meaning of an orthonormal set. Now let me prove a Pythagorean theorem. See, you start from an orthonormal set in X, a finite orthonormal set, f1, f2. So f1, f2, fn. So a finite orthonormal set in X, and G is an arbitrary element in X. Okay, then you have this very important identity. So what is this identity? You consider norm G square. That is obtained by these two sums. Summation j equal to 1 to n mod fj g square plus norm, the distance between, the norm of the difference, g minus this quantity. Okay. So this is the Pythagoras theorem. Let me prove this. This is a very important result. This is something which we will use everywhere in this. So just keep in your mind this identity. And this identity follows from the orthonormality of FJs. So that's why it's a Pythagorean theorem. Now, the proof is very simple. You just denote this quantity, the quantity inside this norm, this quantity. This is a linear combination of Fj. Look at this. Inner product Fjg is a scalar. So it's a linear combination of Fj. So you just denote it by G tilde. So G tilde equal to a linear combination of Fj. Since X is a linear space, any linear combination of elements will be again there. So this is an element in X. Now you compute the norm G square, norm G tilde square. So by definition, norm G tilde square is G tilde, inner product G tilde, G tilde. Now just substitute the definition of for G tilde. So the first thing will be summation J over J, Fj, G, Fj. And the second thing is again the same, but I use the indices by I just to keep in, tell you that there will be off diagonal entries. There will be F1 with F2 kind inner product will be there. But essentially that will not contribute to this sum because Fj with Fi will be 0 when J not equal to I. Okay. So essentially only the same, diagonal terms will come into picture. So now I use linearity and conjugate linearity. So here by conjugate linearity, I can take this summation outside with a bar. And by linearity, I can take this sum outside with as it is. So now Fjg bar will be there, Fjg will be there. So that gives you mod Fjg square. And Fj will be 1. So it will not contribute. So that's the thing. So you obtain norm G tilde equal to this summation. Similarly, inner product G tilde will obtain the same thing. Now it's only a simple computation. Now what you do, you just compute this norm square. So you write it here, and you know that the second entry is G tilde. So by notation, so it is norm G minus G tilde square. Now again, by definition, this inner product G minus G tilde with G minus D tilde. Now by linearity, it is norm G square plus norm G tilde square minus 2 into real part of G tilde. Now keep in your mind that G tilde is this. So its real part is also this. And norm G tilde square is also this. They are same. So these two quantities are same, but there will be a minus 2 of that. So that will give you norm G square minus this. So that's a proof. Okay. So what you obtain is that this identity. Now we will see certain consequence of this identity very soon. Now, again, one more thing, if you have infinitely many elements here also, then also this is true. I will come back to that later. But what is the consequence here? You look at here. So this quantity is always non-negative, okay? Because it's a norm square. Therefore, this quantity will be always less than or equal to this quantity because you are adding a non-negative quantity to obtain this. So that is what is called Bessel's inequality. If Fj of X is an orthonormal set in X, then this sum will be always bounded by norm G square. Again, we can generalize this into infinite setting later. So this is a very important inequality called Bessel's inequality. So these are the two important identities, inequalities and identity which we need. Pythagorean identity, this one, and the Bessel's inequality, this one. Okay. Now using this, we are going to obtain the famous Cauchy-Schwarz inequality. It tells you that for every f and g here in an inner product space, absolute value of the inner product fg is bounded by norm f into norm g. Let me prove this. If f or g are 0, then both sides is 0. If f is 0, this side is 0 and this side is 0. So you have equality. Suppose f is non-zero. If f is non-zero, you can consider f by norm f to be f1. Then it is a singleton set which is non-zero and have norm 1. Therefore, it is orthonormal by definition. So an orthonormal set just need inner product should be 0 whenever you have two distinct things. So here you have only one of norm 1. So that is an orthonormal set. Now we apply Bessel's inequality with n equal to 1. See, recall that Bessel's inequality is true for an orthonormal set and for any G belongs to X. You have this identity. If n equal to 1, that means inner product F1 G absolute value square will be bounded by norm G square. So we apply that here. You obtain mod F1 G square is bounded by norm G square. Now just apply the definition of F1, that is F by norm F. So you will obtain this inequality. This is Schwarz inequality, Cauchy-Schwarz inequality. Mod Fg will be less than or equal to norm F into norm G. Now the natural question, when do you have equality? So when do you have equality here? So equality here means you have equality here. That by a backward computation, you will obtain the equality here means you have equality in the Bessel's inequality. So you have equality in the Bessel's inequality with F1 for the singleton set F1. So if you have equality in the Bessel's inequality, just go back to your Pythagorean theorem. Equality in the Bessel's inequality means this quantity and this quantity are same. These two quantities are same. See, if these two quantities are same, whatever you are taking this quantity, that should be 0. Because these two quantities are same, so that gets cancelled and this you will get 0. That means G should be, so this is 0 means norm of something is 0. By definition, norm of something is 0 will give you the quantity inside this will be 0. So that's what we are going to obtain. So equality holds exactly when equality in Bessel's inequality with F1 and G. This makes norm G minus inner product F1 G F1 should be 0. That means G is a scalar multiple of F. So this will give you G is a scalar multiple of F. So that means equality holds exactly when F and G are linearly dependent. So that's the specialty of Cauchy-Schwarz inequality. Now let us come to the consequence of geometrical structure out of this Cauchy-Schwarz inequality. So if you take two non-zero vectors, by Cauchy-Schwarz inequality, you will obtain that F by norm F into G by norm G is bounded by 1. The absolute value is bounded by 1. You just divide by norm F and norm G, you obtain this. So, what's the meaning of that? The absolute value of a complex number is less than or equal to 1. Therefore, its real part should be lying between -1 and 1. Now you see that the function, cosine function cos t is a bijection from the intervals 0, pi and -1, 1. So you have an element, the real part of this quantity in the interval -1, 1. Because this is a bijection, there is a unique theta in this interval such that cos theta is this. Cos theta equal to real part of this. So recall our Euclidean geometry, you had cos theta equal to inner product A dot B by, dot product A dot B by mod A into mod B. You have exactly similar thing here. Cos theta equal to this one, and you got an angle theta. Angle theta here. So this angle, you define this to be the angle between F and G. But remember that we are in an abstract setting now. Your inner product space can be L2 space, can be C01, can be anything. So you are getting angle between functions, angle between equivalence class of functions, angle between sequences, angle between everything. So not merely vectors. Okay, so that means you are able to obtain the geometrical structure in an abstract setting. So that is the advantage of having this Cauchy-Schwarz inequality and the inner product. Now the topological structures. Yeah. Now let us come to the most important part of the story. So we already introduced the notation norm F. Now we consider the map F going to norm F. Let us prove certain properties of this. Norm F will be always non-negative. That is evident from the definition because norm F is defined to be in the positive square root of FF. That is always non-negative. And norm F equals 0 if and only if F equals 0 because norm F equals 0 means inner product FF equals 0. Therefore, F equals 0 by definition of inner product. So the first property is evident. Now the second property, norm F, it is known as triangle inequality. Norm F plus G less than or equal to norm F into norm F plus norm G for all F and G in X. For this, you consider norm F plus G square. By definition, it is inner product F plus G with an F plus G. By a simple computation, you will obtain that this is equal to norm F square plus norm G square plus 2 into real part of Fg. This is something we obtained when we proved parallelogram identity. Now, any real part of a complex number is bounded by its absolute value. So this is bounded by its absolute value of inner product Fg. But by Cauchy-Schwarz inequality, the absolute value of Fg is bounded by norm F into norm G. So the whole quantity is bounded by norm F square plus norm G square plus 2 into norm F norm G. But the last thing is norm F plus norm G all square. So what we obtain is that norm f plus g all square is bounded by norm f plus norm g all square. That means norm f plus g is bounded by norm f plus norm g for all g. So this is triangle inequality. And the last one is very easy. Norm alpha f is mod alpha into norm f for all f belongs. Now, these three properties, in fact, this function f going to norm f, satisfying 1 to 3, satisfying these three properties is known as a norm. Okay. In any linear space, if you have a function with these three properties, you call it as a norm. And linear space equipped with a norm is called a norm linear space. Now, in fact, the function norm plays exactly the role of the absolute value function in the complex plane. So, how does the absolute value function behave in the complex plane? You have non-negativity, you have this property, you have triangle inequality, the classical one, and this is of course mode that is straightforward. Okay, so absolute value function, whatever absolute value function does in the complex plane, that is the role of norm in the abstract norm linear space. As absolute value function gives a distance between two complex numbers is obtained by absolute value of z minus w. Similarly, here it gives a general distance, something called metric. dfg you define to be norm f minus g. This defines a metric or a distance on x. So whenever you have a norm, you have a distance. So every inner product space, in the usual way, you have a norm induced by the inner product. And every norm gives you a metric. So in that way, every inner product space is a metric space. And you know that every metric space is a topological space with the topology induced by the open unit balls and so on. Open balls and so on. Okay. So this gives you the topological structure on an inner product space. An inner product space naturally equipped with a norm induced by the inner product. And this norm gives you a metric, and metric will give you a topology. That is the topological structure here. Now, another important thing, you consider this second and third property. Remember that inner product space is equipped with a linear structure, an algebraic structure. That means there is a vector addition and a scalar multiplication. These two properties tells you the interplay between the norm and the vector space operations, the addition and scalar multiplications. Okay, and as a consequence of this, you will obtain that this map f going to norm f is actually continuous with respect to the metric given by the norm in the inner product space and usual topology in the real line. That means if f and g, there's a notational problem. This map, notation is correct. This map fg going to f plus g and alpha f going to alpha f, they are actually continuous. That means fn converges to f and gn converges to g will give you fn plus gn converges to f plus g. That follows from here using the triangle inequality. And similarly, fn converges to f and alpha n converges to alpha, gives you alpha n converges to alpha f. That means this is a very important thing. See, in a vector space, you have an algebraic operations at vector addition and scalar multiplication. And this gives you continuity quite naturally. If you have a norm, then these operations are continuous. That's the consequence of these 2 and 3. Now, using Cauchy-Schwarz inequality, you can also prove the continuity of the inner products. That is also important. See, you just go back to the Cauchy-Schwarz inequality. Yeah, look at this. So you treat inner product as a function. So fn converges to f and gn converges to g. From this inequality, you will get inner product fn and inner product fn gn will converge to inner product fg by simple triangle inequality. So what you have is that you have the inner product is also continuous with respect to the norm. Now, so what is the advantage of having this? See, now let us summarize what we did so far. In a linear space, you only have algebraic operations where you can talk about finite linear combinations. But once it is an inner product space, an additional structure is coming, the geometric structure is coming out of the inner product, and also the inner product gives you a topology in this way. So once you have a metric induced by the inner product, then you can talk about convergence of sequences, Cauchy sequences, infinite series. Therefore, you can talk about infinite linear combinations. That's the thing. And you can also talk about continuous linear maps and so on. So, if every Cauchy sequence in a metric space is convergent, we call it a complete metric space, just like R or C. Now, in a normed space, if it is complete with respect to the metric induced by the norm, then it is called a Banach space. And you know that every inner product space, you have a norm induced by the inner product. And if it is a complete with respect to that norm, that means if it is a Banach space with respect to the norm, induced norm, then it is called a Hilbert space. So this is the definition of Hilbert space. So let me just make these remarks once again. You can see that a metric space is simply a non-empty set with a metric. You don't have any algebraic structure there. It can be any non-empty set. You can give a metric in any non-empty set. No algebraic structure is expected in a metric space. But in a normed space, we already have an algebraic structure of a vector space and a topological structure due to the metric induced by the norm. And also this norm is compatible with the algebraic operation by triangle inequality and the other one. And in an inner product, we have all these things, and in addition, we have a geometric structure due to the inner product. Now, a very large part of functional analysis is the interplay between these different kinds of structures: algebraic structure and topological structure, analytic structure, and the geometric structure and their interplay. So that is a more interesting part of this. So let me just got couple of results in this spirit. So one result is that every finite dimensional non-dimensional linear space is complete, and hence is a Banach space. And in particular, every finite dimensional linear product space will be a Hilbert space. You can see that, finite dimensionality is purely an algebraic concept. Okay, it has nothing to do with the topological structure or the norm of the space. But Banach space, being complete, is a property obtained using the norm and the analytical structure or the metric structure. So that tells you how the algebraic structure and this analytical structure are interrelated. Another result you can see, every linear map on a finite dimensional non-linear space is continuous. So continuity coming for free. Your linear map, you're assuming that you have a linear map on a finite dimensional space. That's all. You don't assume anything else. Linearity is purely an algebraic concept, and finite dimensionality is purely an algebraic concept. And continuity, a topological notion coming for free. So that's the result. So in all these above results, we get conclusions based on the analytic structure, that means completeness and continuity, with an algebraic assumption, that means finite dimensionality. In the setting of a non-linear space, this is another thing, which I already mentioned. One can consider infinite series of this form, because you already have a linear structure, so you can talk about finite sums, and you have a metric, therefore you can talk about the convergence. Therefore, you can consider about infinite linear combinations, and so on. So, but this is not possible in an arbitrary vector space. Another thing I already mentioned, using continuity and linearity of the inner product, we can interchange the infinite summation and the inner product. See, earlier we proved that we observed that we can interchange the finite sum from this variable, from the second variable. But G infinite series, you denote it by some limit of the nth partial sum. But limit you can take out because of the continuity of the inner product. Then by linearity, you can take the finite sum. Then again, apply limit, you will obtain this. So you can interchange the infinite sums here in the second variable. You can do it in the first variable also, but a bar will come. That's the only difference. Now let us go back to the examples and see which all of them are complete or gives you a Hilbert space. Look at the first example, H equal to Cn. We know that this is a finite dimensional space, and we have already seen that every finite dimensional space is complete. Therefore, it's a Hilbert space. So this gives you the first example for a Hilbert space. Now the second example, C00. Here you don't have finite dimensionality. It's actually an infinite dimensional vector space. So in fact, this is not complete. You can actually consider a sequence like this and prove that it's a Cauchy sequence. And you can do some technical details to obtain that this sequence has no limit in this C0, in this space. So this is not complete. Whatever I denoted by X will be incomplete. Whatever I denoted by H will be complete. So now H equal to L to N, I denoted it by X, therefore it will be complete. In fact, the completeness can be proved using some standard arguments, but let me skip the proof actually here. A little bit techniques are involved, but it's a standard argument. You start from a Cauchy sequence in L to N, and then you prove that each component wise it will be a Cauchy sequence in the complex plane. And since complex plane is complete, you will have a limit for that. And using all these limits, you form a vector and prove that it is in L2N and convergence happens. That's a standard argument, but let me skip the proof and all. But this gives you the most important example of a Hilbert space. Now this one, x equal to 0, C01, you can see that it is not complete. You can consider this sequence, for example. Suppose this is this point is 1 by 2. I mean, yes. So use the sequence which Fn, which is 0 till 1 by 2, and 1 by 2 plus 1 by n, it is this line, and after that it is 1. So you can see that Fn is a Cauchy sequence, and limit, the point-wise limit will exist, and that will not be continuous at the point 1 by 2. And later you can prove that, it will not have any limit in C01. But remember, it is not the point-wise limit, but something else. Now, the most important Hilbert space, H equal L2 0 1. Again, let me skip the proof for completeness, but this is a Hilbert space with, and a very important one for, as far as the applications are concerned, this is the most important Hilbert space. Okay. Whenever you deal with finite energy signals in signal processing, or whenever you deal with problems connected with Fourier series, you will end up with such a space, L2 space. But let me mention one more thing. Here I only introduced L2 of closed interval 0, 1. But this you can change to any arbitrary interval. For example, minus pi or 0 to pi. Or you can even go beyond finite measure space. You can consider L2 of R itself. But when you consider spaces with infinite measure, then the theories will be a little bit different. But whatever is true for closed interval 0, 1 will be true for any set with finite measure. You can rewrite it by any closed and boundary interval. Okay, this is a Hilbert space. And the last one is obviously a Hilbert space because it's a finite dimensional space. Okay, so it is of no interest for the time. Yeah, now let me just recall what the Pythagorean theorems which we proved. I will not prove it here now, just take. So what is the Pythagorean theorem? You consider a countably infinite orthonormal set. So earlier we had only finite set, but now you take a countably infinite orthonormal set in X, and G is an arbitrary element. Then the same argument will give you that summation j equal to 1 to n mod fj g square plus norm g minus summation j equal to 1 to n inner product fj g fj norm square is equal to norm g square. The same argument, just denote this by g tilde and compute whatever the proof which we did. So you will obtain this. Now look at here. Again, as a consequence, if this quantity is non-negative, you know that this is a norm square, it is always non-negative. Therefore, this quantity, the first quantity, will be less than or equal to norm g square for every n. That is important. We have an infinite set here. So for every n, you have this inequality. Therefore, and the right hand side is independent of n. Therefore, if you apply limit n tends to infinity, then also this inequality will satisfy. So you will obtain the Bessel's inequality as a consequence. So summation j equal to 1 to infinity mod fj g whole square is less than or equal to norm g square. So this is a very important thing. Just apply limit and obtain this. Okay. So this is the Bessel's inequality, the infinite portion. Now proof is more or less we discussed it. Now we see when does equality holds in Bessel's inequality. Okay. Just go back here. Suppose equality holds here. Equality holds here means as n tends to infinity, this quantity, the first term, and the term on the right hand side becomes equal. I mean, as n tends to infinity, this goes to this. That means what? As n tends to infinity, this second term goes to 0. What is the meaning of that? Norm g minus a sequence goes to 0 as n tends to infinity. That means this sequence converges to g. That means what? As limit n tends to infinity, what is this? So that means you have equality here. That means g is equal to this. So equality holds exactly when g equal to summation fjg fg. Infinite sum. So that's a very important thing. Equality holds in Bessel's inequality if and only if this happens. Now, remark. So you start from an orthonormal set in X. It gives by Bessel's inequality, you have a sequence fjg in L2. See, what is Bessel's inequality? It tells you that given this orthonormal set, this quantity, this sequence, this series is bounded by norm G square. This is always finite. Therefore, this quantity is finite. That means this sequence is square summable. So we get a square summable sequence FJG. Okay. So orthonormal set is fixed. For every G, you have a sequence in L2N. Now we do the other way. Suppose G is equal to this, some alpha J Fj, an infinite series. Then by a simple computation and interchange of this, I mean, you can compute that these alpha J's are obtained to be Fjg itself. That means if G is this infinite series, then these coefficients alpha J's are precisely inner product Fjg. And therefore it is in L2N. Okay? That means if G is an infinite series like this, then these coefficients are in L2N. Now, what about the converse? Suppose you have something in L2N. So, something in L2N, a sequence in L2N. Can we find a corresponding G here? So, here what we did, corresponding to each G, here you obtained an element in L2N. Can you do the converse? Corresponding to each alpha J in L2N, can you find a G here? So, let us address this question. But for that, we need completeness. That means you cannot do it in an arbitrary inner product space. Instead, you have to do it in a Hilbert space. So you start from an orthonormal set in a Hilbert space H. And you start from any alpha J in L2N, any sequence in L2N, then this infinite series will converge to some element in H. The convergence is easy to establish now because we are in a Hilbert space. It suffices to prove that this series is Cauchy. I mean, the nth partial sum of this is Cauchy. Every Cauchy sequence is convergent in a Hilbert space. So that is easy because you take the nth partial sum and compute the norm Sn minus Sn square. You'll obtain that that is equal to m plus 1 to n mod alpha j square. Here we use that alpha j comes from L to n. Therefore, this series is convergent and this comes as the difference of the nth partial sums. Therefore, it will be Cauchy. So using that, you will obtain that Sn is Cauchy, hence it is convergent. The proof is straightforward. Now we cannot drop completeness. You can see examples here. Let me not discuss that. So completeness is very important here. You need to work on a Hilbert space. So this is a well-known Rees-Fisher theorem. Now let me come to a very important part, the final stage of the story. So we have seen that you start from an orthonormal set in a Hilbert space H, say Fj, and a G belongs to H. Then this sequence is in L2N. That's what we have seen by Bessel's inequality. Inner product Fjg is in L2N. And also, this is in L2N by Rees-Fisher theorem. You apply Rees-Fisher theorem for alpha j, instead of alpha j, you plug here this. Then this quantity will converge. This series will converge. That's what Rees-Fisher theorem. But it will converge to some G tilde. You don't know it will converge to G. That need not happen. It will converge to some G tilde. Okay? But what you know is inner product Fj G tilde and inner product Fj G will be equal for all G. That is easy because just plug the definition of G tilde here. G tilde is this infinite series. You interchange the sum. So finally you will end up with Fjg. So what you have is that given an orthonormal set, this series will always converge in Hilbert space, but that need not converge to G. That will converge to something G tilde with the property that Fj G tilde and Fjg are equal. That means Fj inner product Fj with G tilde minus G equal to 0 for all G. But it does not imply that G equal to G tilde. For example, if you consider L2N and you consider the standard orthonormal set E2N, I mean, we are taking only in the even part, I mean, E2, E4, etc. I mean, one at the second place, one at the fourth place, and so on. So then it's an orthonormal set, okay? And you start, instead of G, you consider this sequence in L2N. So Fjg, you have E2j with this. If you compute, you will obtain that, you will obtain this. 0, 1 by 2, 0, 1 by 4, and so on. You are not getting G back. Your G was 1, 1 by 2, 1 by 3, 1 by 4, etc. But you are getting G tilde, which is not equal to G. So G need not be equal to G tilde. Why this happens? Because Fj G tilde equal to Fj G for every J does not imply G equal to G tilde. This is the reason. If it implies, then you. So in other words, this happens because Fj is not maximal, need not be maximal as an orthonormal set. That means Fj h tilde equals 0 for every j need not imply that h is 0. So because of that lack of maximality, we have this problem. For example, this is not maximal. There are non-trivial vectors which is orthogonal to each element, each vector in this orthonormal set. That's the problem. So to eradicate that problem, let's consider the notion of orthonormal basis. What is an orthonormal basis? A collection of it is a maximal orthonormal set in a Hilbert space. This is called an orthonormal basis. What do you mean by maximal maximal orthonormal set? If this is contained inside, contained in another orthonormal set, then that set should coincide with this. So there should not be any bigger, strictly bigger orthonormal set which contains this or containing this properly. Or in other words, that tells you that if f alpha f, the inner product is 0 for all alpha, then that f should be 0. Only the 0 vector should be orthogonal to each f alpha here. So that's what you call an orthonormal basis. And why it is called an orthonormal basis? Because of this representation. If you have an orthonormal basis, you have this G, you will get back G. That's something you will get just now. But before that, let me mention one more thing. In general, an orthonormal basis need not be countable. Okay? But you have some positive results here. Suppose that f alpha is an orthonormal set. You start from an orthonormal set in an inner product space. Then for every f belongs to X, this set where inner product f alpha f non-zero. So f alpha such that inner product f alpha is non-zero is at most countable. So even though f alpha can be uncountable, but the set where inner product f alpha non-zero is at most countable. Okay, so that is a very important thing because these are the things which we use to represent f. Now you look at here. If f alpha is an orthonormal set in a Hilbert space, H, and for f belongs to H, yeah, you start from an orthonormal set in a Hilbert space H and start from f belongs to H. Then the set EF is countable. You have already observed here that this is countable. So EF such that f alpha with f alpha f, inner product f alpha non-zero is countable. You denote it by f1, f2, etc. This is a countable set now. Then this summation converges to some G belongs to H. So we have already seen that this converges, right? So by Rees-Fisher theorem, this will converge because FJF is now in L2 by Bessel's inequality, and any such things will converge. And this G will satisfy the property that inner product f alpha with f minus G equals 0 for all alpha. This is obtained simply by applying Rees-Fisher theorem with an orthonormal set this, and the L2 element is FJF. So what you have is here, given an orthonormal set, you start from any f belongs to H, you have a countable set where this inner product is non-zero, you denote it by f1, f2, etc. And you form the infinite series, summation j equal to 1 to infinity fj, f, fj. It will converge to some g. Moreover, that g will satisfy this, inner product f alpha, f minus g equal to 0 for all alpha. Now look at here. What happens if f alpha forms an orthonormal basis? Then f equal to g. Because f alpha f minus g equal to 0 for all alpha should imply that f minus g equals 0. That gives you f equal to g. So as a consequence, you get this. If in the above situation, that means in a Hilbert space, if f alpha is an orthonormal basis in H, then we have f is equal to summation j equal to 1 to infinity inner product fj, f, fg. This is a very important identity. This expression is known as abstract Fourier series. The proof is quite trivial. I mean, I have already explained more or less the proof. So this is what you call abstract Fourier series. I will tell you the consequences. Now, this is, you just go back to the Bessel's inequality. So if you recall the Bessel's inequality, just look at here. Yeah, equality holds in Bessel's inequality exactly when this happens. Look at this. You have this identity. That happens if and only if equality holds here. So in the orthonormal set condition, we obtained already this. So therefore we have this. So we already obtained this. This is the criteria for equality in the Bessel's inequality. Therefore you have this. Norm f square equal to. So you are able to compute the norm using these coefficients. So that's the advantage. Okay. So we obtained these two important expressions known as abstract Fourier expansion and Parseval's formula. Now, there are plenty of examples for orthonormal basis. One can construct orthonormal basis using standard process due to Gram-Schmidt. You start from any linearly independent set and apply a Gram-Schmidt process to get an orthonormal set with the same span, and keep on doing that, you will end up with orthonormal basis. And we already seen the standard example in L2N, the standard basis and thing. In fact, there are more examples, but I will only discuss one particular example because of our specific reason. You consider H equal to the Hilbert space L2 minus pi. So I already mentioned that you can consider any compact interval minus. So in particular, I consider minus pi. Consider the sequence f and t given by e raised to int by root 2 pi with t belongs to minus pi. Here n varying in the set of all integers, n equals 0, plus or minus 1, plus or minus 2, and so on. Then proving orthogonality is easy. Or means proving orthonormality is easy here. You take inner product means it will be integral of e raised to m minus n t, and when m equal to n, it will be 1, and you'll get 1. Integral will be 1. I mean 2 pi gets cancelled. And when m not equal to n, you will, with the standard integration, you will get that it is 0. Orthonormality is easy, but getting orthonormal basis, I mean, getting that this is an orthonormal basis, this forms an orthonormal basis is not straightforward, but it's a fact that it is an orthonormal basis for the Hilbert space H. Okay. Now, what is the consequence? By above results, this is an orthonormal basis. Therefore, you have this expression, the abstract Fourier representation, f equal to summation minus infinity equal to infinity fn fn for every f in L2 minus pi. Now let me use this notation. See, inner part fn f is integral fn t bar f, where fn t is this, right? So let me just use a notation here, f hat n, which is denoted by this integral. This is actually inner product fn f with some scalar multiple. So this is known as the Fourier coefficients, f hat n. So with this notation, what you obtain is f of t is equal to summation minus infinity to infinity f hat n into e raised to int. See, fn is e power int, so that scalar will come. So you obtain this. So remember our first problem, we began with a couple of problems, vibrating sink problem and heat conduction problem, where we ended up with some issues related to the series like this. This is known as the Fourier series. Okay, so we developed all the function analysis tools, and finally we ended up with such a thing. And what is the meaning of this series? Remember, it does not mean that for each t, the right hand side series converges to f of t. That's not the meaning. It means that for every f in L2, the nth partial sum will converge to f in the L2 sense. What is the L2 sense? The norm in L2, which is given by the integration. So recall our question at the beginning regarding the converse issues of Fourier series. This arose in the heat conduction problem and vibrating problem. So this above result gives a positive answer under certain particular setting. So the approximation is only purely in the L2 sense. So there are functions with divergent Fourier series. This has to do with the notion of convergence and smoothness of the function. That means when I say that divergent Fourier series, convergence with respect to what sense? That's a very important problem. Okay, so you don't have convergence, point-wise convergence. You don't have uniform convergence. Is there any problem? Okay, so you cannot expect convergence point-wise. You cannot expect convergence, uniform convergence, or anything. Here you have only convergence in the L2 sense. But even we have continuous functions with divergent Fourier series in the point-wise sense. Okay, there are several positive and negative results in this connection, in this direction. What happens here? You have two choices. Either you relax the notion of convergence. You don't demand for uniform convergence. You just demand for some convergence in the lighter sense, like L2 sense or something. Then you will get convergence for a large class of functions. The other option is that you impose some additional condition on the function. You assume that the function is nice enough, twice differentiable, like that. Then you will get some kind of convergence with some other notion. I mean, a better convergence. So, in fact, most of the important problems, I mean, most of the important notions, converse notions, notion of functions and everything, most of them in the classical analysis arose from the convergence issues of Fourier series. That is very important. So the identity, and now you consider the identity, this is what we obtained just now. This has several practical applications. For example, if you consider signal processing, okay, so this is very important. See, this is used to retrieve the signal. So suppose your function is signal is represented by some f. You will be sending the Fourier coefficients f hat. Fourier coefficient you can compute by some fast algorithm like FFT, fast Fourier transform algorithm, and you can send this f hat ends. So from this f hat end, you need to retrieve the original signal. So that's what your f. So this expression is being used to retrieve the signal in the practical. So there are several other practical problems where Fourier series come quite naturally, and therefore the function analysis tools are applicable there. There are other important, okay, so one more thing, there are other important class of orthogonal bases such as orthogonal polynomials like Chebyshev polynomial, Legendre polynomial and so on, or also such as wavelet bases and several other things. So depending on our practical issue, practical problem, you will use the representation with respect to different bases. The abstract Fourier representation which I obtained here, yeah, this expression and the abstract Parseval's formula, this works for any orthonormal basis. In particular, it works for Fourier basis. It also works for wavelet basis, orthogonal basis, polynomial basis, and several other bases. And that is why this is applicable in a wider sense. Okay, so let me summarize. Several important notions in classical analysis were developed to settle the convergence issues of Fourier series. So let me end with this quote from the book by Rajendra Bhatia. It tells you that Fourier series are not just tools for physicists and examples for the mathematicians. They are directly responsible for the development of nearly one half of mathematics over the last 2 centuries. You can agree or disagree with this, but I do enjoy doing Fourier series. So these are some references, some very important references. The first one is due to Barry Simon. He is a mathematical physicist. He has written recently a comprehensive course in analysis. There are 5-part book series. It is available in Amazon. In fact, it discusses most of the things in analysis, starting from basic real analysis and ending up with mathematical physics problems and several other things. You will enjoy reading this, and also included several historical details, and it's fun reading them. Now, the second one is a book by Rajendra Bhatia, which I mentioned just now, Fourier series. Its second edition is available now. It tells you the whole development of Fourier series from the physics problems and how it contributed to the classical analysis. And then using that Fourier series, how the classical analysis notions were developed and how these notions were useful in the abstract areas of mathematics like number theory and several other areas. And then how they became applicable in problems in chemistry and several other things. It's really worth reading. Such a short textbook, a small textbook actually. And the last one is, of course, a familiar book for all of you, Function Analysis by Balmohan V. Limai. So I hope I'm in time. So thank you very much for your patience. I would love to have questions.